LWE.
Thanks for the introduction, and thanks for the invitation, Daniel and Chris. So I'm going to speak about this algebraic algorithm for LWE. So it's going to be a kind of a new approach. Well, it's a new approach, unusual approach to assess the security of LWE. So it's a joint work with Martin Albrecht, Carlos Cid, and Jean-Charles Faugère. And actually, Martin bring to us this lattices stuff. So we are working on mainly on cryptanalysis using Grosvenor basis, and it appears that it can be used also in this context. So very quickly, so I'm going to consider the classical LWE problem. So this is the definition that we saw. So just to fix the notation, so n is going to be the dimension of my matrix, and m the length. So I'm going to consider the problem of actually recovering this secret. So you can see this problem of learning with errors as decoding a random linear code with a special type of distribution. And so I will again simplify the distribution here. So it's a discrete Gaussian, as we all know. But for me, I will only assume that each component of the error is small, and so you have q the size and this alpha the parameters. And so we all know that this is secure. So you have the connection to worst case gap is VP. This alpha q is big enough. And so what Martin brings us to us, and what has been interesting for me and Jean-Charles is a formulation of the problem in terms of algebraic equation due to Aurora and Gay. And so it's decoding a linear code. So it's solving a system of linear equation with noise. And so the idea of Aurora and Gay was to generate from this a set of algebraic equation without noise, but no more linear. And what is very nice with this result of Aurora and Gay is that, well, it gives you a very simple algorithm, which is exponential in, so it's in the square of alpha q, and it turns to be sub-exponential if the parameters is slightly less to what the security reduction require. So in some sense, it's a bit frustrating for Aurora Gay, because they were very close to have a sub-exponential algorithm for solving gap SVP. But on the other hand, from the point of view of the designer, it's very satisfying, because Regev derives this condition on the security, and it was discovered in a different way that actually you require this condition on the distribution. So today, what I will consider is a simple version of this problem I'm going to talk, where the error is very small and so uniform in an interval. So I'm going to consider what is called the binary error LWE by Daniele and Chris. And so in this context, so it's the same problem, decoding, but the error here, each component of the error is going to be 0 or 1. So like for LWE, so you can prove the hardness of this variant. So you have a connection to a hard lattice problem. But here the security parameter, what gives you the security is not this size of the error. It's going to be the number of sample, which will give you the security. And applying this Aurora-Gay algorithm, you can prove that you can solve this problem in polynomial time if you have a n square sample. Okay? And here, well, this is the limit for the security. Okay? So, so far so good. So for me, it's very nice. So it's the type of typical things that we use to do with Jean-Charles. So we reduce a given problem or the security of a crypto system to the solving of a nonlinear system of equation, and after we try to solve it. What is going to be a bit different here from what we are doing in general is that in this context, we will try to not break given parameters, because actually we have no parameters. We will try to derive actually a bound on the complexity. So what we are going to, we will do this by using Gromner basis. And so we will use the modeling of Aurora-Gay that I'm going to show you. It's very easy. And so the idea of Aurora-Gay is to do linearization. Okay, so for binary LWE, you have you're on degree 2, so you have a product of this form. And so for each variable, you associate a new one. So you get a system of linear equation. And so if you have enough linear equation, so n squared, then you can solve the system. Well, of course, you can perform Gaussian elimination if the equations that you are going to generate are linearly independent. And really the very nice, the strong point of the paper of Aurora-Gay is to show that if you generate sufficiently many linear equations, you do the linearization, then you will actually be able to solve the problem in this way. So the rank of the system is going to be sufficiently big. So you get really a proof of the algorithm. So in the context of binary LWE, you can do, well, this linearization, but you have this number of samples. So the questions that we try to address with this approach is how much the security is going to decrease or to increase, how it will change in function of this upper bound, for which you have your polynomial time algorithm, and the security bound, the security limit given in the paper. And so if you have less than this number of samples, that this number of equation, then you cannot do linearization. And so you have to do, to compute a Gromner basis. Okay? So I will give you some few elements on the complexity of computing Gromner basis. Just know, because I guess you are maybe not very familiar. Well, I assume that I will introduce quickly Gromner basis and the complexity. So you have a system of polynomial equation, nonlinear, and so your goal is to find the variety associated to this. So you want to find the common zero of the polynomial equation. So in one way, when you have a lot of equations, you do linearization, and in general, you can compute a Gromner basis. So Gromner basis will be a, so the truck again will, is going to be a special generator set of your polynomial ideal, which will allow you to compute the set of solutions. So once you have a granular basis, then you can compute the variety associated to your ideal. So we have an algorithm for doing this. So it starts with Bruno Broberger. And so now the modern view of computing granular basis is to do linear algebra. And so this view is important to bound, well, to compute it efficiently, but also to give some bound on the complexity. So the important object to consider when you compute a granular basis with linear algebra is this Macaulay matrix. Okay? So what you are going to do is to, so Fi are the generator of your ideal, and you will consider a multiple of your polynomials. So here I multiply each polynomial by a term. This is going to give me a polynomial of degree d, okay, for some d. And so I put the coefficient of this polynomial in a matrix, okay? So the columns are the monomials of degree smaller than d, with d as a bound, and the row are the multiple of my polynomial. And so we know that if you perform a row echelon form on this matrix for d big enough, then you can compute a granular basis. So it allows you to give a rough bound on the cost of computing a granular basis. It's going to be the cost of performing the linear algebra on a matrix which is sufficiently big. So the cost of computing the granular basis is going to be exponential in this degree of regularity. So in this talk, I assume that the variety and the ideal that I'm considering are zero-dimensional. So I have a finite number of solutions. So you have this simple expression for the complexity, and now the question is, how big is this degree of regularity? Well, in general, actually, it's difficult to know what is the degree of regularity. And so to compute the degree of regularity for a given system, there is no more. The solution is to compute the granular basis in general. But we have a specific family. So if you do some assumption on the systems that you consider, for which we can compute explicitly this degree of regularity. So this polynomial, this special family are called the semi-regular sequences. So assuming that the polynomials are semi-regular, then you can compute explicitly what is the degree of regularity. To do this, you consider this power series, which is actually the generating series of the rank defect of your Macaulay matrix. So the coefficient will encode the rank defect. So the number of columns minus the number of linearly independent rows. And from this power series, so you can expand it, you can read the coefficient of regularity, the degree of regularity. It's the index of the first coefficient, which is 0 or smaller than 0. So this is a small example. And so you can see here that the degree of regularity is 4. Okay? And so these semi-regular sequences, so you can see the conditions that we impose. It's in some sense the generic behavior of the rank defect of the Macaulay matrix. So for this family, we know explicitly what is the rank defect of the Macaulay matrix that you are considering. And so we know all what we need to compute the complexity of Grosvenor basis. Okay? So this is the reference. Yeah?
You actually need to compute this number? Isn't it enough to have an upper bound?
Good. Yeah, it's enough to have an upper bound. But for the moment, I don't say exactly how I can get an upper bound. So this is going to be my next slide. For the moment, I'm saying that for this family, with this condition, then we know what is the behavior of the rank defect of the Macaulay matrix. And so I want to point here a difficult point with these semi-regular sequences is that actually we don't know if such sequence exists. So a famous conjecture, which is known as Froberg conjecture, is yes, these semi-regular sequences exist. So this is kind of frustrating because this gives you more or less what is the typical behavior for the complexity, semi-regular sequence, for computing a Grosvenor basis. If you sample randomly your equation, for sure, if you compute the Grosvenor basis, it's going to be, the Hilbert series is going to be exactly this one. The issue is that up to now, it's difficult to find for any parameters an explicit family which have this Hilbert series. Okay? And so actually, yeah, you can, here you have the Hilbert series, so you can put special parameters and get the degree of regularity and so the complexity. But what is more useful for what I'm going to present is to have bound on the degree of regularity. And so for semi-regular sequences, we have a bunch of approximation on the degree of regularity. And for instance, for this type of system, we know that the degree of regularity is a constant times n. And so you can see here that in function of the ratio, this constant decreases. So this is one example of behavior for the degree of regularity. And actually the global picture for equation of degree 2 is as follows. So this is the linearization bound. Okay? So you know that if you have a system of quadratic equation, then if you have this number of sample number of equation, then with high probability, you can solve in polynomial time. Actually, so this is with the linearization. If you compute a Grosvenor basis with a slightly less equation, we know that it's a polynomial time if you have this number of sample. And so we know that if m is O of n, it's exponential. And if it is soft O of n, it's sub-exponential. So for semi-regular system of equation, we have kind of the exact behavior on the complexity. And what I would like to point out is that, well, in practice, you have if you sample randomly the equation, then you have this. And for a zero-dimensional system, you have not the doubly exponential behavior, which maybe you are afraid when you hear the word of Grosvenor basis. Okay? So how we can apply this type of things to to binary LWE. Once we will have the system, you will see it's pretty obvious. But for the moment, we have no system, but it's very easy. So the approach of Aurora can be summarized in one slide. So now I'm coming back to my problem, to binary error LWE, to your problem. So I want to solve it using Aurora equation. So I know that I have this equality, okay, and so each error is 0, 1. And it's I take this polynomial which vanish in 0, 1, and I write this set of equation. So I just evaluate affine form whose unknown are the coefficient of the secret, which give me a set of m quadratic equation in n variables over fq. Okay? And so once we have this, then we can derive bound on the complexity of solving this set of equation. But to derive this bound on the complexity, I will assume that the system that I'm generating here is semi-regular. Okay? So this is my assumption. And so assuming this,
the assumption false, or you just don't know that it's true?
I don't know. I will talk about the assumption just after. So if you assume that you have this semi-regularity condition, then you can derive for various parameters on the number of samples how the complexity is going to change. So under this assumption, it's pretty straightforward. So you get a complexity with respect to this approach. So if it is slightly bigger than O of n log n, then it is sub-exponential. But it remains exponential for 2n and for what was advised in the security proof. It remains exponential, this approach, but after it decreases with the number of samples. Okay? And so, of course, you are all saying, well, what about this assumption? So this is the question. So we need to know if it is reasonable to assume that the system that I'm generating are semi-regular. So one way to do this is to do experiments for n as big as you can, and so we perform experiments for different type of parameters, and so it seems to work. It means that the maximum degree reached during the computation is exactly the degree which is predicted by the assumption. Of course, here I'm not attacking given parameters. So from the slide that you saw before, it's exponential for the parameters, for the type of parameters used with the security proof. So you are not going to solve it in practice. What I derive is asymptotics, and so I want to be, I would like to be sure that the bounds that I'm giving are working for n big enough. So we try to investigate this assumption. So first, this is a difficult question. And so if we can solve it, it goes beyond this this application on binary error LWE. So this is something which is really central when you are doing grammar basis computation. We are always using this type of assumption when we want to derive a complexity bound, this genericity. So here, I'm actually considering something slightly different. So I'm trying to prove the assumption not for a random system of equations, but for something which has some structure. So the equations that I'm considering are power of linear forms. So it's not something completely random. But it appears that this type of system of equation has been investigated by the author of the conjecture. And he also believes that this system of equation are indeed semi-regular, and actually he proved it in some restricted cases. So when the number of sample m is equal to n plus 1. So we try to go and prove the assumption in some restricted cases. So I will finish with this to show you what is the difficulty here. So let's say we take the simple case. So we want to prove the assumption at the smallest degree. So we want to prove that the equations are linearly independent. Okay? And so I'm taking the maximum number of equations smaller than the bound which is given by Aurora-Gay. And so I want to prove that these equations are linearly independent. So the tool that I'm going to use is Schwarzschild. So what I want to prove is that so it's a wrong condition. So I have a determinant. So I want to prove that a determinant is non-zero with a good probability. So it's a wrong condition. So you have the polynomial, but the issue is to find one particular example for which your polynomial is non-zero. Okay? And so this is the tricky point of proving this assumption, is that you have to find a specific family for which you can prove that if you take this matrix J, then it is indeed of the rank, when you generate the system, that you expect. So we can do it in some particular cases, but in general it's a complete mess. And so I think that we have not exactly the good tool to address this question. So I will come to my conclusion here. So I'm not too much sure. It's okay. So we have a paper describing this approach. So we can derive bound also for LWE, but you have also to assume some genericity condition. Okay, and so I will finish with some open question and for you. So I'm kind of looking for comments and about this, because what we did, so the modeling is very naive, and so we know that if you want to get something, if you want to go beyond this, we need to go a bit deeper in the problem. So as Daniel mentioned, so you need to know more lattices. So for us, we need we need some help to have some additional properties that we can use for the modeling to go a bit further. And so the other open question is to prove this assumption. So I think it's of independent interest. So it's a classical issue in Schwarzschild lemma. You want to prove that something is non-zero. But here we want to construct family of matrices which have a specific rank. So for the moment, we are trying to take a very simple example of matrix, see what is the Macaulay system, Macaulay matrix corresponding, and trying to prove this by hand. So it's clear that we are going to be able to prove maybe in restricted cases, but it's probably not possible to prove the full assumption in this way. And well, I will finish by mentioning a paper of Pierre-Alain Fouque and Paul Kirchner, and he will give, I think he will give a presentation tomorrow, and an even better result on binary error LWE, and more generally on LWE. That's all.
So for the binary LWE, you take this quadratic polynomial of these linear forms, and you get quadratic assisted quadratic polynomials. If your noise is coming from a larger set size B, then you get a degree B polynomial. So how do the runtimes and the number of samples roughly behave as B increases?
So that's good question. So I was giving the same talk 3 weeks ago, and Vadim asked me the same question. And so the technical issue is that to derive this type of result, so for each family of n and each degree, so you have to do an analysis on the series. So you have to do, so you have analytic tools, and so you have to, it's not automatic. And so if you say, well, I want, instead of quadratic, I want a degree 3, then I have, we have to do all the analysis again. So it's to give you precisely what is the behavior, it's difficult. But the global trend, I can. So if it is degree D, then I can linearize with n of D. So I am going to be a polynomial. So I replace here with slightly smaller number of samples, so D minus 1. So here I will still be exponential. Okay, so the constant will change. And if what is surprising is if you have m log n, so you still sub-exponential. Let's say for d equal 3. So this I know for d equals 3. D equals 4. For any d, so if d is not a constant, it's the techniques are different. Yeah.
So I don't know a lot about this area, so this very well could be a stupid question, but it seems like some of the tools you're using here are some of the same tools that are used to build and break, like specifically like multivariate quadratic-based crypto systems.
Exactly.
So do you think that we could? Is there a way to prove some kind of connection between those hardness assumptions and LWE? I mean, that they're not. It's not like obvious that there is a connection, but do you think that a connection could exist?
So it's not thank you a lot for the question, because I skipped this point. So I was mentioning at some point that so this type of tools is used to attack various type of scheme. So typically multivariate and code-based scheme. But in general, when we are on this problem, then we have not this behavior. So assuming that the system is semi-regular, it's kind of a worst-case assumption. So most of the time, if the system that we have behave like this, then we give up. So it means that it's secure. And so the difference here is that the degree that you are going to have is much smaller. So typically, if you have systems which are coming from HFE, or multivariate scheme, then you know that the degree of regularity is going to be constant when you increase the parameters. And so I think the fundamental difference here is that in this case you have no proof of security. Okay, so you have the scheme, and it's possible that you have some hidden structure. So, and in this case of LWE, when you attack the scheme, when you try to break LWE, then you have to solve search LWE, and with no structure at all. So it's random matrix. So you have to go directly with the difficult problem. So in these cases, we have a different type of problem, different type of structure that we can exploit. But, well, coming back to the talk of this morning, here, for compact Michaelis version, what we use, so coding and so coding scheme and what I show here, it's very close. And here what we have been able to use is that the matrix which are constructing in Michaelis, the generator matrix, they are a block structure, and each block is, let's say, cyclic or dyadic, as some kind of structure. And so in this case, we can exploit. And so if the system has some symmetries in general, then we have a specific bond in function of the symmetries. So we have degree of regularity which can be much smaller.
Hello, this is Madeline calling you from Charlottesville, Virginia. The new lab is coming to your town. All your towns, actually.
All right, let's thank Ludovic again.